The next speaker is Stefan Gurke. He will speak, now he is in Slovakia, yes? Slovak University
Yes.
of Technology, and he will speak about some graph about which you probably will give more explanation. Welcome.
Yes, thank you, Ilya, for the introduction. First of all, I would like to say that this work is joined with Misha Klin and Matan Zivav, so you will be probably not surprised if you will see some kind of reflection of Misha Klin's work or his style of work. So this talk will be about a graph which was independently discovered by several people, and it will be about a graph which is strongly regular. So a lot of different things from algebraic graph theory and several combinatorial structure will meet in this one object, which looks like this. Actually, the edges of this graph are the colored edges, and the dashed edges are just displaying that you can draw this picture on the background of a dodecahedron. So this is the object we will somehow inspect here. Okay, a few words about the history. Already Norman Biggs was interested in the question whether there are parameter sets, feasible parameter sets for strongly regular graphs which are realizable, but there is no vertex transitive strongly regular graph on that set. Or oppositely, that he was maybe thinking about the case that all feasible parameter sets are realizable by a vertex transitive strongly regular graph. But the answer was given for his question in less than 2-3 years when Paulus started the complete enumeration of strongly regular graphs of order 25 and 26. His enumeration at that time contained some inaccuracies, so the search was completed independently by Rozenfeld, and that time was clear evidently that none of the strongly regular graphs of order 26 are vertex transitive. So this is why the graph carries the names Paulus and Rozenfeld. And also, if you take the PhD thesis of Don Thompson, then you can find this graph in a construction in quite different manner using designs. So let's start from the definition of strongly regular graphs, although probably everybody knows here what they are. So a graph which is regular and has the property that the number of common neighbor of every two adjacent vertices is constant, and we will denote this number by lambda, and also the number of common neighbors for non-adjacent vertices is a constant number. And then we will speak about strongly regular graphs with parameters nk, lambda, mu, where n is the number of vertices and k is the valency of the graph. So later on this week, you will hear a lot of talks concerning DESA graphs. So I am just noticing that strongly regular graphs are a particular case of DESA graphs. One of the probably most famous strongly regular graphs is the Petersen graph. You can see 10 vertices, each vertex has 3 neighbors. None of the adjacent vertices have common neighbors, and if you take any 2 non-adjacent vertices, they are joined by exactly 1 path of length 2. That means that is equivalent to saying that they have precisely 1 common neighbor. So about this question I already talked in the motivation. So if we look through the data collected on the web page of Andries Brouwer concerning strongly regular graphs, you can see that on all the feasible small parameter sets up to 25 vertices, you can find very symmetric graphs, very symmetric in the sense of vertex transitivity. And due to the exhaustive search or complete enumeration of graphs with the parameter set 26, 10, 3, 4, we can soon realize that this is the first or the smallest parameter set where there is no vertex transitive graph. And we know that there are precisely 10 non-isomorphic graphs with these parameters. If you consider their automorphism groups, then we can see that most of them have very small groups as automorphism groups, and there is one which has 120 automorphisms, so in some sense it is the most symmetric among them, and this will be our graph. The group is isomorphic to the alternating group of order 5, direct product with the group of order 2, and this group maybe will be visible in a few cases in this talk, because I'm going to describe this graph in different not languages, but in different models. So I will construct it maybe 3-4 different times. So in the previous talks, we have seen a lot of color graphs. So by a color graph, we just mean a complete graph with loops and a complete digraph, because we will regard each edge as 2 oppositely oriented darts. And we just assign colors to each dart or loop. And this kind of object is called color graph. And the number of used colors is the rank of the color graph. And the coherent configuration is a special kind of color graph. Also, I think since previous 2 talks, we're using implicitly that everybody knows what the coherent configuration is, then I don't know whether I can assume this. So there are 2 quite easy properties to understand, that the colors which are used on the loops are not used elsewhere, and whenever I am using a color on some dart, then on the opposite dart it is the same color every time. Same in the sense that if, for example, I have a red dart and the opposite dart is green, that at each place I am having a red dart, the opposite dart is green. So I can create pairs of colors, but also this can be translated into the language of relations, and this will mean that I'm decomposing the complete binary relation into some relations, and if I have a relation, then its transpose relation is also contained in the decomposition. The third property of the coherent configuration was already used by Pascal several times, that if I fix a pair of vertices in some order, then I can count the colored triangles, and if these numbers are constant and depends just on the concrete choice of the triple of colors, then I have a coherent configuration. And if I have the situation that all the colors used on the loops are the same, then in fact we have a homogeneous coherent configuration. And usually that object is called an association scheme. Okay, and a natural source of coherent configuration and association scheme are permutation groups. If you take a permutation group and you create its two orbits, or also some places are called orbitals, then you are obtaining an object which satisfies all three properties of being coherent configuration. So you can, in this manner, obtain a lot of coherent configurations, and these are called so-called Schurian coherent configurations. On the other hand, also there exist coherent configurations which are not coming from these in this way, and these are called non-Schurian. And usually, if you inspect non-Schurian coherent configuration, you can obtain some nice surprises, some combinatorial things which cannot be obtained directly from permutation groups. Or so it is always a nice challenge to investigate non-Schurian coherent configuration. Okay, so by fusions or by union of relations from a coherent configuration, of course, you can obtain different graphs. For example, if you take the dihedral group of order 10 and degree 5 in this concrete presentation, then this permutation group has 12 two orbits. Some of them are written on the slide, and by taking the union of the two orbits 01, 04, 05, and 06, you will obtain the Petersen graph. The two orbit 01 corresponds to the edges of the outer 5 cycle. The two orbit 04 corresponds to the inner 5 cycle, and by gluing together darts from the two orbits 05 and 06, you are obtaining the undirected edges between the two 5 cycles. So in this fashion, you can really create dozens of graphs, and in many cases, you can, if you have an association scheme or coherent configuration, you can explain the existence of graph in these terms, or oppositely, if you have a graph, then you can take a look on underlying coherent configuration, which you can obtain by the Weisfelder-Lehmann stabilization. So you can create bridges between many different combinatorial structures just based on the knowledge of the coherent configuration behind them. So in this manner, we will provide the first construction of the Paulus-Rozenfeld-Thompson graph. So let's take the alternating group of degree 5. You can generate it, for example, using these two permutations. And as we have seen, the graph, the OR graph is not vertex transitive, so you can. It is expected that you will not be able to describe the set of vertices just in a uniform manner. So let's consider here two kinds of objects. First, the objects will be ordered pairs of distinct elements of the set 0 up to 4. And the second kind will be the pentagons on the vertex set 0, 4. And consider just one pentagon and its orbit under this group. You will obtain in this manner 6 pentagons, and it is easy to count the number of ordered pairs you defined is just 5 by 4, so 20. So altogether we consider 26 objects which will be corresponding to our vertices. So if you fix, for example, the pentagon in the middle of this picture, then the alternating group maps it to 5 different pentagons. Thus, the orbit contains 6 pentagons. Now we can define adjacency between them. Where is that slide when I am? Aha, okay, I'm not saying anywhere that. Okay, so we will define the graph in such manner that these 26 objects are the vertices of them, and 2 vertices will be adjacent whenever the first coordinate of the pairs is the same, or the second coordinate of the pairs is the same, or the pair is contained in the pentagon as an edge. So this how we can, and also 2 ordered pairs will be adjacent when one is transposed of the others. So here it goes, but all these things can be explained in the terms of the association scheme, or sorry, coherent configuration behind it. That coherent configuration is Schurian, as it is coming from the alternating group of degree 5. One can count that its rank is 14, so it has 14 2 orbits, and it contains as merging 2 copies of our strongly regular graph. And by the construction, it is easy to see that the group of automorphisms contains the alternating group of degree 5, and also after proving that it contains a strongly regular graph, then it is easy to see that it has to be the Paulus-Rozenfeld-Thompson graph among the list of all graphs with the same parameter, because all other strongly regular graphs with these parameters have a group of automorphism of much smaller size. So this description gives a precise description how to glue together the two orbits into our graph, and this is the explanation of the colors appearing on the first figure. So all this information can be obtained just by the knowledge of the coherent configuration and its merging, which gives the requested graph. So here we can see again how the colors appear. And just I noticed that the 20 vertices, which are vertices of the dodecahedron in this picture, are the ordered pairs, and the 6 additional vertices are corresponding to the pentagons. And if you consider the subgraph which you obtain on the pairs of vertices, on the pairs from the set 0, 4, then you obtain this kind of picture where the black edges are in fact cliques. So all the vertices which are arranged on this picture in the same row or in the same column are forming a clique of size 4, and they are just displayed by one thick black line. So as we could see, our graph is somehow related to the dodecahedron, because dodecahedron lives in the same coherent configuration, and we can obtain two edge disjoint dodecahedrons inside the coherent configuration by unions of orbits. And also, if you are looking for more objects inside that coherent configuration, then you can find by union of two orbits the directed strongly regular graphs with these two displayed parameters. First one is the known Kautsky graph on 20 vertices. And maybe more interesting objects inside the same coherent configuration is that the Brouwer's 0,2 graph, which is usually then denoted by N6.3, lives inside this coherent configuration, and this graph is a graph with parameters 0 and 2. That means that the number of common neighbors of each pair of vertices is either 0 or 2. And among all such graphs, this one is the unique vertex transitive and non-bipartite of valency 6. And we can, in the terms of this coherent configuration, it is easy to figure out how to obtain that Brouwer's graph. Just take a dodecahedron and you can create 4 tuples of vertices or 4 subsets of vertices which are at mutual distance 3. So here, for example, you can see the blue vertices, and you will add a for-click among these blue vertices, and also the same you will do with the vertices of the same color, and you will obtain the Brouwer's graph. Now, we would like to describe our graph based on the dodecahedron, similarly as we did it with the Brouwer's graph. So take the skeleton of the dodecahedral graph. Again, we have to consider two types of vertices. First type will be the actual vertices of the dodecahedron, and the second type of vertices will be formed or will be corresponding to so-called Petri polygons in the dodecahedron. I will show in the picture what a Petri polygon is. I'm not going to provide a precise definition. So with these two types of vertices, we can explain our graph, and two vertices of type 1, that's which are the vertices of the dodecahedron, they will be adjacent in our graph if and only if their distance was 3 or 5 in the dodecahedron. And the vertex is adjacent to the Petri polygon when it is contained inside of the Petri polygon. And in such manner, we will obtain our graph. So what a Petri polygon is? If you are familiar with the combinatorial maps, then you probably know it. If not, then take an embedding, for example, this dodecahedron graph into a plane, and you can traverse the edges or the faces of this map by such walls that if you start at some place, you will go along on one side of an edge, and in the middle of the edge, you switch the side and continues in the same direction. If you will do this, then at some moment you will come back into your original position. So if you will do this with all possibility, then you will decompose the graph into Petri polygons. Here, the dodecahedron can be decomposed into 6 Petri polygons, and maybe the easiest to see on the black Petri polygon that it misses two pentagons. In this case, the black polygon, Petri polygon misses the outer pentagon and also the inner pentagon.
Stefan, may I ask you?
Yes.
Yeah. What is the motivation to use such kind of polygons? I mean, in general.
It provides some kind of duality, but I'm not an expert on combinatorial maps. But those who are interested in combinatorial maps can say a lot about them. So I am just touching this topic, but without deeper knowledge on Petri polygons.
I see. So you mean that next time we need to invite Roman Nidel to explain us
or Josef Širáň, or
oh yeah, right.
Martin Matches. So there are a lot of experts on this topic.
Okay.
So
okay,
they will say more about this. But thank you for the question. Yeah. Okay, so this is another language how to explain our graph. And of course, if we can explain it in the term of dodecahedron, then just using simply the dual terms or duality in combinatorial maps, you can start the same consideration from the icosahedron, as the dodecahedron and the icosahedron are dual to each other. So you can consider the triangles in the icosahedron and the antipodal pairs of vertices in the icosahedron, because they are in one-to-one correspondence with the previous objects, and just simply to create the same adjacency by that duality between these two objects. So, for example, here is again a combinatorial embedding into the plane of the icosahedron. The triangles corresponds to the vertices of the dodecahedron. So here we are considering the triangles, and the antipodal pairs of vertices are those which are corresponding to Petri polygons. And here Petri polygon will be adjacent, or sorry, an antipodal pair will be adjacent to a triangle when they have a non-trivial intersection. So it is easy to transit from the dodecahedron to the icosahedron, so I think I will not talk about more details. So I'm coming to the last type of construction, and this construction will use switching, true graphs, Paley graphs, and a lot of interesting objects from algebraic graph theory. So let's start from Paley graphs. If you take a finite field of order Q, where Q is congruent 1 modulo 4, then you can create such a graph that the vertices will be just the elements of the field, and the two elements will be joined by an edge whenever their difference is a non-zero square in the field. And these graphs are easy to see, or to prove, that are strongly regular graphs with the shown parameters. And the important for us is that the parameter k is just double of the parameter mu. It will be important, and we will come back to it. Our interest is in the Paley graph, where Q is 25, but to understand the full construction will be easier to start to consider the case when Q is equal to 9. So take the Paley graph of order 9 and add to it one extra vertex. I think this graph without this extra vertex already appeared in Pascal's talk. So you have seen this picture before, and now you will do with this graph switching. Switching which I am using here is just usual switching, that you select two cells, two subsets of the vertices, and you will switch the edges between these two cells. That means that if there was an edge going from, for example, here on this picture, from vertex 0 to vertex 3, then in the switched graph there will be no such edge. And for example, here there was no edge between 0 and 4. So in the switched graph, there will be an edge between these two vertices. And inside the cells, nothing is going to be changed. So I am removing the edges between them and adding all the edges which were non-edges between two cells in the original graph. So I'm getting, in this case, a quite messy picture. So I'm creating the complement of this graph in order to see at least something on this picture. And probably a few of you already noticed that I just obtained the Petersen graph, but in a very unusual manner, or in unusual drawing. So here I am showing that really we obtained the Petersen graph. And all this job can be done just by a single step from the Paley graph extended by an isolated vertex. When you switch the graph by selecting an independent set of size 3 in the Paley graph. So again, just right after the switching, you maybe do not recognize the Petersen graph, but actually it is. So this is the way how we can obtain from the Paley graph of order 9 the Petersen graph. And just by using the same procedure, we can obtain from the Paley graph of order 25 our graph, or the graph which is called the Paulus-Rozenfeld-Thompson. So take the Paley graph, add a new vertex, and now select two disjoint 5 coccyx and switch the graph, and the result will be what we was interested in. Why
Stefan, I'm sorry, but I just wonder by whom this construction was suggested. I mean, from Paley graph.
Misha Klein knows a lot of stuff, or he's creating a lot of bridges between different combinatorial objects. So he, at some moment, he recognizes just from the underlying coherent configuration that which are the set of objects which can be related to that one, which one is inspected by him.
I see.
So he has this insight that, which is, I think, quite amazing that he can recognize this connection between different combinatorial objects. But yes, the essence is to inspect the coherent configuration behind.
Stefan, can I ask you also a question? When you write two disjoint 5 coccyx, this means in the new graph, or you take this coccyx in the Paley graph?
In the Paley graph.
Okay.
So like here, you are taking the Paley graph, adding to it a new vertex. Now, in the Paley graph of order 25, you have many 5 coccyx. You have to select two of them independently. In this joint. And just to do the same switching.
Mm-hmm. I also have a short question. When you do this switching, do you know in which orbit the point at infinity will end up? Orbit of length 6 or length 20? That's not, maybe not that important, but.
Good question.
Probably I don't know. Okay, never mind.
Yeah, good question, actually. Thank you. I will think about it. Okay, so why this stuff work is hidden in the objects called two graphs, because two graphs are invariant on this switching. Invariant, I will explain in what sense. So a two graph is a set of points and a set of three subsets of points having the property that all four subsets of vertices contains even number of triples from the triples. So this is some kind of block design and not a graph. So first I have to warn, if somebody sees these objects for the first time, that I have to warn him that this is not a graph, this is just an incidence structure. And but this incidence structure can be related to graphs in a nice manner, that whenever you have a usual undirected graph, then you can simply select the three subsets of vertices in which the induced subgraph contains an odd number of edges. So in this manner, from each graph you can obtain a two graph, and this two graph will be invariant under the switching what we were doing with the graphs. It is easy to see because if the tree subset is contained inside one cell, then of course switching doesn't change anything in that tree subset. And the only non-trivial thing what can happen, that one vertex is in one cell and the remaining two vertices are in the second cell, then it is easy to see that the number of edges inside this triangle after switching has the same parity. It is just a very easy combinatorics or number theory. It's just basic. So this will be somehow justifying our concept. Okay, so if we, for example, say take a 5-cycle with an isolated point, then you can select all the triples which contains odd number of edges on the graph induced by those three vertices, and you will obtain a two graph. Yes, that's what I was talking about a few seconds ago. So the important thing is that you can bijectively map the switching classes and the two graphs to each other. So for example, if you start with the empty graph and you are doing all the switching, all the possible switching, you will obtain altogether 8 graphs, but all these 8 graphs corresponds to the two graph on 4 vertices which has no blocks. Further, two graph is called regular if it forms a two's design. That means that each pair of vertices is contained in the same number of blocks. And now we are able to formulate a theorem which was proved by Schultz, that if we have a strongly regular graph with whose parameters satisfy the condition that k is a double of the mu, then you can create the corresponding two graph by adding a new vertex vertex, new isolated vertex, and the obtained two graph will be regular. So I will probably skip this one. And in fact, we were doing this job with the Paley graph of order 9 on previous slides. So this can be done also for the order 25. And what is interesting is that on 26 vertices, there are just 4 regular two graphs. This result is still a computer result, and it would be nice to provide computer-free proof that this is really the case, that we have just 4 different regular two graphs, and to find a proof in algebraic terms or combinatorics. And among these 4 regular two graphs on 26 vertices, the most symmetric is that one which is obtained from the Paley graph of order 25 by adding a new vertex. And its group of automorphisms is a vertex transitive with a very nice group, PSL225 extended by semi-directly by C2. And we will use this information on a little bit later on. So what we have seen is on these small examples is valid in general, that if you have a regular two graph with v plus 1 vertices, and it is coming from a strongly regular graph of order v with parameters that satisfy the condition, then the corresponding switching class always contains a primitive strongly regular graph. Primitive strongly regular graph is such one that neither itself, neither its component is disconnected. So for example, the Petersen graph and its complement are connected. And the proof contains, or the existence of such graphs is strongly related to the existence of cliques in two graphs. And by a clique in a two graph, we mean a subset of vertices that each tree subset that can be created with these vertices belongs to the tree subset of the two graph. So if we consider the regular two graph obtained from the Paley graph, or which is related to the Paley graph of order 25, then this two graph contains 65 maximal cliques which are of size 6. It is easy to see 15 of them because you can take the co-cliques or cliques of size in the Paley graph, and just by extending it by one vertex by the newly added vertex. And the information that this regular two graph is vertex transitive, you can simply use that through each vertex the number of maximal cliques is the same. So that's how you can obtain the precise number of maximal cliques of size 6 in this regular two graph. And if we do the same job with this regular two graph, and if we start from the complement of the Paley graph, and it is well known that the complement of the Paley graph of order 25 is isomorphic to the original Paley graph. So you can do the same job twice, and you can in this manner obtain cliques of size, maximal cliques of size 6 in one regular 2 graph and the other regular 2 graph. So you will obtain an incidence structure on 26 points and with blocks of size 6, and altogether you have 130 blocks like this. And this incidence structure is a Steiner system with parameters 3, 6, 26. And this Steiner system is a well-known object, which is the unique inversive plane of order 5, or also known under the name Michelian plane of order 5. And this object is also very nice and has a quite large group of automorphisms. It is a three-transitive group, isomorphic to projective semilinear group 225. So again, we come to some, I don't want to say other part of combinatorics, but we can see that a lot of things are related to each other in very clever manner. So for those who do not know what the inversive plane is, it's just a combinatorial analog of some stuff related to geometry, and that's why the blocks in this language are called circles. So this inversive plane satisfies three quite natural properties. So if you have three different points, then there is precisely one circle going through all of them. So you can just see the correspondence with the geometry. Also, if you have a point and another point, and a circle which is going just one of them, then there is a unique circle passing through both points that intersect the first circle at that point. And there are at least 4 points that exist a point circle pair for which the point is not incidence on the circle, and every circle has at least 1 point. So this is just to avoid some triviality. So again, one can consider the related association scheme and to tell more about that object. And I think I have now something like left like 3 minutes or so. So maybe it is worth to mention that that we can connect our construction also to the so-called Schultz double cover. Here is the precise definition, but on picture maybe it will be easier to understand that. For example, the Schultz double cover of a pentagon you obtaining in a manner that you are taking two isomorphic copies of the pentagon. To each copy you add one new vertex. This new vertex will be joined to the vertices of the corresponding copy, and you will add the edges between the two copies of the original graph in such manner that two vertices will be joined when they were not joined in the original copy and they do not correspond to the same vertex. So for example, 1 and 1 prime will be not connected because the isomorphism is between them, but 1 is joined to 3 prime and 4 prime because there was no edge between 1 and 3 and 1 and 4. So if you write down the Schultz double cover of a pentagon in much nicer manner, then you will obtain the icosahedron. So again, one more bridge is created between stuff in algebraic graph theory. So maybe it's worth mentioning the consequences or the results obtained by Schulte in this direction. Actually, originally Schulte suggested this construction to create transitive extensions of permutation groups. So again, construction which is related to more deeper things in algebraic graph theory. And maybe it's worth mentioning a result by Surovsky that if we start from a Paley graph of order Q and making it a Schultz double cover, then the full group of automorphisms of this graph will be the direct product of the group of order 2 and the projective special semilinear group of order Q or of degree Q. And in the smallest case, smallest interesting case, when Q is 5, then the A5 is precisely this group. So this how all how a lot of different things in algebraic graph theory meet in the Paulus-Rozenfeld-Thompson graph. So, and at this moment, I would like to thank you for your attention.
Thank you very much for a good talk and very interesting. And we have time maybe for one small question before the next talk, or comment or remark.
Can I ask a question, Ilya?
Yeah, certainly.
Okay, Istvan, can you go to page 49?
49,
You showed
yes.
4 graphs on 26. You
Yes.
mentioned that one of them has an automorphism group, which you mentioned there. Do you know for the automorphism group of the other 3 candidates?
Yes, I can find you it just that they are not much smaller, but smaller. This one has 15,600 and others have something like 3,000. But let me find it.
They are known, and from there you can derive the structure of the graph.
Yes.
And if you just start with your hypothesis, is it clear that the automorphism group is relatively big, or is there no reason to think group theoretically about this question to get a computer-free proof? I mean,
I don't know actually.
Obvious reason.
So probably it's worth thinking that that why all these 4 are so symmetric.
Yeah. Okay. Thank you.
Thank you for that question.
I have one question, if I can.
Yes.
Very small.
Yeah, it's quick. I really like the talk. Thank you very much. I just wanted to ask, did you try to apply the similar construction on some other Paley graph to obtain some graph with other parameters, not just on this relation Petersen and Paulus?
Yes, Misha is working with Dennis Apple on the next one for where Q is not 11 but 11 square. So this is somehow the next interesting step, and they are working on it probably for 2-3 years, and we will see when the results will be published. So.
Okay. Thank you.
You're welcome.
Thank you once more. Let us thank the speaker again. And because we should start the next talk,